All right, well, welcome to the end of the first week of differential equations, man. We are flying. It always surprises me how quickly it starts going once we get going. Today's plan, I do want to talk a little bit more about these linear first order differential equations because there are going to be some issues with them. So far, you've seen it's pretty easy, right? It's just a matter of following the process to get the solutions. But there are a couple of little kinks that we need to discuss. So I want to talk about that. But then I want to turn our attention to a different kind of differential equation, ones we call separable. We'll see what the process is for that. So by the end of this first week, you'll already know how to handle two different types of differential equations. Both of them are first order, but at least we've already got those down. But before I do that, I want to open it up to you guys. Any questions on the homework or anything else we've talked about so far? We can definitely do that, Victor. Let me go ahead and write this down. So number 18 from 2.1. All right, any other homework questions we want to look at? All right, well, let me pull that up here and we'll give it a go. And then Victor, you're saying number 47 was very linear algebra to you? Well, we'll look at that. We'll take a peek at that after. And I'm not surprised. Like we talked about last time, there are a lot of similarities between these. So, all right. Well, let me go ahead and share my screen so that we can all see what number 18 is. And then, oh, hold on. Let me get Ralph's here. 1.3, number 7 and 13. Sorry, I didn't see those. Okay. So let's pull up the book and we'll take a peek at these. All right, so here's the one from 2.1, and we're looking at number 18, right? And so number 18 just says find the general solution. All right, so we know what we need to do here, right? We just got to hope that it's one of the forms that we know. So really right now, the only form we know is linear first order. So is this linear first order? Can you write it in the form y prime plus p of x times y equals g of x or f of x or whatever they called it? Are we of that form?
Yeah, weird.
Yeah. What do we have to do to it first before we? Yeah, Victor already put it in the chat. We just need to divide by x, and if we could divide it by x, then we're going to have just the y prime all by itself. All right, so let me pull up a whiteboard and let's walk through this one. All right, so we had xy prime plus 1 plus 2x squared y equals x cubed e to the minus x squared. So we'll divide by x. So I'm going to go ahead and split them into the two pieces, divide each of them by x instead of making it one fraction, because I think that'll be a little bit easier for us when it comes time to actually solve it. All right, so that first algebra step just gets us to the point where it's in the form we know what to do. All right, so what's our next step? What do we do at this point?
We need to find a solution for a homogeneous.
Okay, so we're going to just look for the solution to the homogeneous. So we're going to pretend that that's 0. I mean, not even pretend, we can just go ahead and do that. So we need to solve this thing. All right, so the process for that, y1 is going to be e to the negative integral of p of x, so 1 over x plus 2x. So that's going to give us negative natural log of x minus x squared And we don't bother with a plus C because all we need is a solution, any solution. So we'll just pick the nice and easy one here where C is equal to 0. All right, but I'm going to simplify this a little bit because I think it will help us when it comes time for us to find U, find the integrating factor. So first of all, let's think about that negative natural log. We can bring that in. So this is going to be e to the natural log of 1 over x minus x squared, which then by the rules of exponents are going to give us e to the natural log of 1 over x divided by e to the x squared. And the e to the natural log of 1 over x just gives us 1 over x. So here is the solution, or a solution, to the homogeneous, 1 over x e to the x squared. All right, so how are we doing so far? We okay with that? As I mentioned last time, remember and make use of your rules of logs because it's going to really, really help when it comes time to simplify. All right, so we got our solution to the homogeneous. Now what do we do?
Need to find U.
Okay, so we need to find U, and how do we find U?
The integral of f of x over y1.
Okay, so it's going to be f of x, the thing that are the non-homogeneous function. So we're going to have x squared e to the minus x squared. And we're going to divide that by y1. Okay, so it's always the f of x divided by the y1. All right, now this one we can definitely simplify. If we flip this over and multiply, it's the same as multiplying by x e to the x squared. The e to the x squared and e to the minus x squared are going to cancel. And then we get x times x squared. So this is just the integral of x cubed, which is x to the 4th over 4. And this one we do need to put the plus c. So there's our integrating factor. All right, so we're almost there. What's the last thing we have to do?
Multiply by y1.
Yep, and we're going to take this thing that we just got, the u, and we're going to multiply it by the y1. So our general solution then is going to be 1 over x e to the x squared times x to the 4th over 4 plus c. So x cubed over 4e to the x squared plus c over x e to the x squared. And there you go. That is the function that satisfies this original differential equation. And we could check it, right? We could differentiate this thing, put that in for the y prime, multiply it by x, take it, multiply it by 1 plus 2x squared, group like terms, and what we should end up with is x cubed e to the minus x squared, if we did it right. But I feel like we're okay in terms of our steps. All right, so how are we feeling about that one? Is that good? And Victor, since you specifically asked for it, I just wanted to confirm that you're good with this and see what happened.
Yeah.
Yeah?
Yeah.
All right. Okay, so again, it's a process. It's the same process every time. It's find a solution to the homogeneous. Then find our integrating factor by doing the f of x over that solution. Then take that integrating factor times the homogeneous solution. All right, so there's number 18. So let's jump back and go look at section 1.3. Ralph asked about numbers 7 and 13 on that. So let me find that. Actually, that'll be faster probably. Okay, so I know I just skipped 7. I got to see what it actually says to do. All right, so in 1 through 11, a direction field is drawn for the given equation. Sketch some integral curves. All right, so integral curves, that just means plot some solutions to this differential equation. All right, well, to do that, let me just really quickly, because I can't draw on this. Oh, actually, I think I can. Check that. Uh-oh. All right, I think I can draw here on the PDF. All right, so here's what I'm going to do. I'm going to draw some solutions, which means I just need to choose a place to start. I think blue works, but let's make it a little thicker. So we'll choose just any place to start. So how about we choose this point first? All right, so let's look and see what the slope field tells us is going to happen. So at this point, I'm going to be going downward, and I'm going to start flattening out. So I'm going to
Just so you know, it's not screen sharing anymore.
Uh-oh, thank you. Let's try that again. All right, can we see it?
Yeah.
Yeah, we're back. All right, thanks, Bradley. I appreciate that. Okay, so again, at this point, I'm going to be going down a little bit, but starting to flatten out. So I'm going to go ahead and just start drawing that. But then notice what happens here. I kind of start going up a little bit, but not a lot. And I go up a little bit more and kind of just settle in there. If I go the other direction on this, kind of following the arrows, it looks like that is a solution here. All right, so let's try another one. Let's do a different color. We'll switch to red. And let's say we start over here. So I'm going to go flat, but notice the arrows start sending me up, but then they start flattening and then bring me down. So I'm going to kind of come down here, but then it starts to flatten out again. And I guess, I don't know, does something like that. So there's another solution. And literally, you just keep choosing different points and you see what has to happen at those different points. So let's take a point that's maybe out here. Okay, so this one's telling us to go up, kind of flatten down, a little bit of oscillation in this direction, up, and then so like there's a third one, and so on and so forth. So that's all we're looking for with a problem like this, is just sort of follow the arrows and see what's going on. But notice that these all have a little bit of oscillation to them. There is some waviness to it. Even here, there was some small waviness, but that shouldn't surprise you. I mean, look at the differential equation, right? It's y prime equals sine of xy. So we're getting the sine of value. So we should definitely see some oscillating between plus and minus 1. And we do see that with some of the solutions. All right, so is that at least a good push for what we're looking for in number 7? Again, I'm going to specifically ask Ralph because he's the one who asked about it. All right, so then what about number 13? All right, so 13, this one says we want to construct a direction field and then plot some integral curves. So this has one more step than what we just did. we want to start by drawing those slopes of tangent lines. So we're going to use this equation to help us do that. So let me go to the whiteboard. All right, so let me clear all this. So let's start by constructing it. So it's y prime equals 2 minus 3xy. So what I'm going to do, well, that's not straight at all. Try that again. That's marginally better. Okay, so here's our axes. And now let's just choose some points and figure out what the slopes are and draw little line segments with those slopes. All right, so how about we go with 0, 0. At 0, 0, if I plug those in for x and y, I get y prime equals 2. So at 0, I need a line segment that has a slope of 2. Let's say that that's 2. All right, so let's move over here, let's say to 1, 0. At 1, 0, that's going to equal 0. So I still get a slope of 2. And it should be pretty clear that no matter where we are on that axis, we're going to keep getting a slope of 2, since the y is always 0. And then similarly, as we go up the y-axis, since x is always 0, all of those things are going to be 2 as well. All right, well, let's get off of 0, 0. Let's get off these axes and plot some other points. So let's actually do these, that these are halves and not ones, because otherwise I'm going to get really crazy slopes really quickly. So let's go to 1, 1 right here. If x and y are both 1, I get 2 minus 3, which is negative 1. So I'm going to get a slope of negative 1 at that point. If I was at, let's say, 1/2, 1/2, half times a half is a quarter, 3 times a quarter is 3/4, 2 minus 3/4 is 1 1/4 or 5/4. So it's still going to have a positive slope. It's just not as steep. So let's make it not quite as steep, right? And we could continue doing this for all kinds of different numbers. If I go x is -1 and y is +1, then I'm going to get 2 plus 3, which is 5. So that's actually quite steep. And I just keep doing this until it starts giving me a picture that kind of makes sense to me. Now, I'm way too lazy to do this. So here's what we're going to do. Let us go over here. We'll go share my browser window. Let's do a search, and we'll just do a slope field generator. We use Desmos's. How about? So this is what I showed you last time. So let's change this so that it's the derivative we were looking at. So we had y prime equals 2 minus 3 times x times y. All right, well, if you look at this graph and you specifically look at what we saw that we had plotted so far, you can see that everything on the axes all have the same slope of 2. Remember how we ran into that slope of -1 over here? Well, there's that guy. Up here, we ran into a slope of 5, so you can see that it's steeper, right? So this gives us a picture of the slope field. And so now you could do the same thing in terms of drawing a graph. Choose a starting point and then see what happens as you go in those directions. So this one, let me do a screenshot real quick. And we'll take it over to, I'm going to open up Paint. So give me 1 second here. All right, so let me share my screen here real quick. Okay, so hopefully you guys are all seeing my Paint window. But we're going to be able to draw this exactly the same way. So like, let's do a blue solution. Actually, let me zoom in a little bit, make this bigger. Oops. Okay, so let's say we're going to start in the origin. So the origin tells us to go upward in this direction. But notice that on the other side, all these things are sending us up as well. That tells me actually that there's going to be some sort of like an asymptote. And the same thing down here. So like that would be a solution if I started there. If I started somewhere else, like how about over here, that's going to send me off in this direction, which then sends me up and up and up and up, and it gets really steep. When I go downward, right, notice that it actually sends us the other way. So like there would be a solution if I started at that point. And you can do this anywhere, right? So the same kind of deal. This is going to send this down. And then this one, since there's like negative slopes, again, it's going to do something like that. So this one's a little bit hard to see probably because we don't get a lot of variation. Whoops, I've drawn all kinds of random crap. We don't get a lot of variation in the slope field. So unlike the other ones, but once you have the slope field, it's the same thing like we did before. All right, let me stop sharing. So is that better for 13? Again, it's same kind of idea as 7. It's just you got to generate it yourself.
That differential equation was definitely first order, but just to be clear, it was not linear, right? Because it had the sign of XY.
So number 7 was not linear, correct. Number 13, the one we just looked at, was.
13 was, okay.
Because 13, let me pull that back up. I think I got it on the whiteboard still. Right, this was number 13. If we rewrote this, we'd have y prime plus 3xy equals 2. And that's definitely linear, right? Because your p of x is 3x, your f of x is 2. And so we know exactly what we would have to do to solve it, right? You find your solution to the homogeneous, make that a integrate minus 3x, put that on e. Then once you get that, divide that into the 2, integrate that thing to get your u, then multiply and blah, blah, blah. So this one is definitely linear first order, but it's non-homogeneous. The other one, y prime equals sine of xy, this is non-linear, still first order. And you're exactly right. The reason that it's non-linear is because the y is in the sign. If it had just been y prime equals sine of x, then this one's linear first order. Because the y, the only y's are in as the y prime, and that's linear.
Cool.
All right, but good question. All right, so.
The other reason why I asked is because the 13 graph, like of our integral curves, it reminded me of tangent, the graph of tangent, a little bit.
Yeah, a little bit. I can see that.
and that's why I thought maybe it was nonlinear.
Yeah. So the resulting function can definitely be nonlinear, even though our function itself was linear, or the differential equation was linear. Right? Like think about, well, okay, think about the one from 2.1. I forget what number it was, 18 or whatever that Victor asked about, the very first one. Remember when we found the solution, that solution had like e to the minus x squareds and all kinds of really random shit in it, right? Definitely not a linear function, but it came from a linear differential equation. So there's a difference between a linear equation and a linear function. Even though we use the word linear for both, they're different creatures. So you can get nonlinear functions as solutions to linear equations. All right, so cool, feeling better, hopefully. Don't forget those first homework sets, they're going to be due Monday night at midnight. And honestly, I think it's just the chapter 1 stuff that's due on Monday. We're definitely ahead of schedule, as I've mentioned. So, but you can, if 2.1, because I don't remember, look at the syllabus or look at Canvas. Whenever 2.1 is due, you know how to do everything in 2.1 now. We've definitely talked about it, with the exception of one little quirky thing that I want to address now. All right, so we cool? We ready to move on to learn a little bit more here? All righty, well then I'm going to go ahead and hop up to the whiteboard and I'll see you guys in just 1 second. All right, so far we've learned that there's a perfectly good technique for solving linear first order, right? Whether they're homogeneous or non-homogeneous, we have a process, and that's awesome, right? But there are some potential issues, and I want to start just with this guy right here. All right, so suppose we have y prime plus 2ty equals t. So let's kind of walk through the process again and remember what we need to do. So it's linear first order. It's already in the right form. So we can jump straight to getting our y1. It's going to be e to the negative integral of 2t dt, which is going to be e to the negative t squared. Right? So fast and easy. So then when we go to get our u, that's going to be the integral of our function t divided by y1, so e to the minus t squared. So this will be the integral of t e to the t squared. You can do a u substitution on that, and you get that that's actually 1/2 e to the t squared plus c. So then we finish this off by multiplying the u times the y1. And so we get that our general solution, e to the minus t squared times 1/2 e to the t squared plus c, which is just 1/2 plus c e to the minus t squared. Right? Okay, so no big deal. Nice and easy process, same thing every time. All right, now let's change this equation just ever so slightly. Ever so slightly. Instead of having it equal t, let's make it equal 1. So still linear first order. It's in the right form. We can go through the process. All right, well, y1 is found exactly the same way. And in fact, it's going to be exactly the same as what we just found. So e to the minus t squared. The fact that we changed what our function was that it was equal to had no bearing on y1. And that should make sense, right? Because y1 is a solution to the homogeneous, so it doesn't matter. It's still going to equal 0, so it's the same form. Oh, that shouldn't be y prime, it should be y. Okay, so cool, right? No big deal. So then let's go get our u. So u in this case is now going to be 1 over e to the t squared, or sorry, minus t squared dt, which is the integral of e to the t squared. And this is when you should go, shit. What's the integral of e to the t squared?
Don't know, can't do it.
So you don't know, you can't do it. It's not a nice function, right? Like this is the classic. This is the one we always show you, e to the x squared. This one, there is no nice antiderivative. Okay, so the question is, what do we do now? Does it mean that there isn't a solution?
Not necessarily. Maybe we could do like a dummy variable situation.
Okay. What do you mean by a dummy variable?
I don't know. Maybe put something in to disguise it for us. Something that we
Okay.
can work with.
Try to pull a math trick.
Yeah.
Yeah, the usual will fool the integral into thinking that it can actually do it.
Yeah, something like
Okay,
that.
I like where you're thinking. Unfortunately, yeah, no, that doesn't work. But it's really tempting at this point to go, well, okay, I can't do the integral of e to the t squared, which must mean there isn't a u, which must mean there isn't a solution. But that's actually not true. It turns out that all linear first order differential equations have a solution. Every single one of them has a solution. We'll actually prove that later when we talk about existence of solutions and uniqueness of solution. But there is a solution. It's just not a nice function. It's not one of the ones that we run into when we're learning calculus. I don't know if you know this. You've probably been told by me and or Larry through the years that like in calculus, we show you the nice functions, but there are way more non-nice functions than there are nice ones. We just kind of trick you into thinking they're all nice. They're all things like inverse tangent or e to the x, or but that's because those are the ones that allow us to teach you the techniques easily. Because this does actually exist. You know how you can find it? I wonder if any of you know what kind of trick we're going to pull. Because it's not a dummy variable trick, although I like that idea.
We could maybe go to polar.
Okay, so polar, that's another good idea. It's not quite what we want. You're getting closer. It's something that you guys all hated. Every single one of you hated this.
Trig sub?
No, but I get it. I didn't realize you all hated trig sub. That makes me sad.
The last thing I can think of is matrix, something to do with a matrix.
We're going to use power series.
Oh.
Was I right? You all hated power series? So here's the deal. We can replace that e to the t squared with a power series. Remember what that is it's turning into a polynomial of infinite degree. But then you can integrate each one of those. So you're going to get a solution as a power series. Now, we're not going to do that. At this point, we're not going to do that, but don't think, okay, good, we don't have to deal with power series, because we will. Later this term, we'll see how sometimes we have to use power series to help us solve equations. But there is a solution. You could actually find it by using power series. Now, this one's actually easy because it's e to the x, and we know the power series for e to the x. So all you'd have to do is replace a t squared for those x's, but you could actually find it as a power series. So sometimes you're going to run into this. You're going to run into something that you actually cannot find an antiderivative for. At this point, what we're going to do is we're just going to leave it like this. We're going to say, okay, well, we're going to get this integral and then a plus c. So our solution is going to be e to the minus t squared times this. So it's going to be e to the minus t squared times this integral plus c e to the minus t squared. So this is just what we're going to do for right now, because we don't want to worry about dealing with the power series and everything. But as I said, we can go ahead and find the power series for e to the t squared. We can then integrate that power series, and that's going to give us a power series for our function. So that's the math trick here. Turns out that that math trick is used all the time. We use power series all the time when we run into something where we don't have any other idea, especially with integrals and derivatives, because you can always integrate and differentiate polynomials, right? It's just they're not super nice. All right, so this is the one sort of, well, we got to cover our butts here kind of deal that's sometimes going to happen. It doesn't mean there isn't a solution, because there is. It's right there. It's just not a nice function. We can create a power series for it, which is what we would do, especially if we want to use technology to help us solve something. Like if we're going to be programming a computer to deal with this, a lot of the technology uses power series, by the way. A lot of the stuff behind the scenes in the black box, it uses power series. All right, so good news, bad news. I guess good news is there's always going to be a solution to any linear first order, and you know the steps to do it, because it's the same steps every time. Solution to the homogeneous, find your integrating factor, multiply. The bad news is sometimes it leads to things, because they're the two integrals, right? We're integrating twice. It's definitely possible that one or both of those integrals are a problem. Well, the workaround is power series. Okay, so check that box. You now know how to solve linear first order. So let's turn our attention to another kind of function, another class of functions, or sorry, equations. And these are, again, first order. But we call these separable equations. So we're still in the first order world. No second derivatives, no third derivatives, nothing like that. And these are just first order. All right, now for it to be separable, you have to be able to have this form. We're going to have some function of y times y prime equals some other function of x or t or whatever. So this is what it means for it to be separable. We have to be able to write it in this form. And sometimes you'll have it exactly in that form. All right, so like for example, we could have y cubed plus y times y prime equals 3x squared plus sine of x. Right, so here's an example of one that's in exactly that form. So this right here is your h of y, and this is your g of x. So when it's already in this form, it's pretty clear. It's pretty easy to see. Sometimes it's not in exactly that form, but can be written in that form. So here's another one. Let's say we had, let's go with y prime equals t over y. So you look at this one and you go, well, wait a minute. I've got a y on the other side. But we can manipulate this easily if we just multiply both sides by y. Then what we've got is y times y prime equals t. And now we do have it separated. It's in this form. So our h of y is just y, and our g of t is just t. All right, so this is what it means for it to be separable, is that by doing algebra, you can turn it into this form. All right, so if it's separable, it turns out that there is a process that we do every time. Just like with the linear first order, there was a process we did every time. And it's actually really, really easy. Because once we're in this form, all we have to do is integrate both sides. If you integrate both sides, and we'll go back to the symbols that we used for antiderivatives, we used the capital letters, hopefully you remember that. But basically, this is going to tell us that h of y is equal to g of x plus c. And hopefully you can see why it's going to satisfy this differential equation. Differentiate both sides. If you differentiate the right, you're going to get g of x. If you differentiate the left, you're going to get h of y, but then there's the chain rule. We have to multiply by the derivative of what's inside. Well, the derivative of what's inside is y prime, and so really what this is, I mean, honestly, this is chain rule backwards. I know it doesn't look like it and it doesn't feel like it, but we're doing chain rule backwards. All right, so the goal with these is to put it into the right form. Put it into this form where all the y's are on one side and all the other variables are on the other side. And then you can integrate each side. So that's why they're called separable, first of all, because we can separate the letters into the two sides. And then once we're there, we just integrate. All right, so let me show you some examples, and you'll see that it's not really that big a deal. Oh, and by the way, we already did this when we solved the linear first order for the homogeneous. I don't know if you guys remember that, but let me just backtrack real quick. When we did the first order homogeneous, so we have y prime plus p of x times y equals 0. If we manipulate this a little bit by moving the p of x term over here, then you divide by y. Because then the next step was we integrated, and that's what gave us the e to the integral of minus p of x. We were making use of the fact that it was separable. In this case, h of y is 1 over y, and g of x is minus p of x. So we actually did this to solve linear first order. We're just now going to extend this technique to help us solve things that are not linear. Right? Like both of these functions are very much not linear. because we have functions of y that we can't separate out like we did before. right,
Is
so-
it still considered separable if the g of x equals 0?
Yep.
Okay.
Yeah, like if this is just a constant,
Yeah.
yeah, it's still separable. I mean, that is a function of x. It's a constant function. So it is possible that there are no, I mean, there's just a number over here, you know, and not necessarily just 0. It could just be, I mean, it could be a 1 or something else. But yeah, even if it was just equal to 0, it's still separable. The key is you can get all your y's together on one side as some function of y times y prime. That's the kicker. The other side is going to be your other variable and constants, or just constant. All right, so let's do some of these. Let's play around with a few of these and see how they work. All right, so we'll go ahead and do one of the ones that I just wrote up here. Let's look at the y prime equals minus t over y. I think I might have done plus t, but we'll do minus t over y in this case. So the first thing you want to do is the algebra to separate it. This one's pretty quick. We just need to multiply both sides by y and turn it into the separable form. So now we just integrate each of these things. So I'm going to get y squared over 2 equals minus t squared over 2 plus c. I'm going to multiply everything by 2 just to get rid of the fractions. So we get y squared equals minus t squared plus c. It's a new arbitrary constant. That's twice the other arbitrary constant. It's still arbitrary. So all right. Now, this is the one thing, or well, this is maybe not the one place, but this is one place where we have to be a little bit careful. And it's if we want to solve for y, we really have to watch out for that, right? Because like if I were to solve for y here, I'd take a square root, but don't forget, there's a plus or minus. So we would get y equals plus or minus the square root of negative t squared plus c. All right, so both of these are perfectly fine for our solutions. And we have names for these different forms. This one, the first one, this is what we call an implicit solution. The second one is an explicit solution. And really all this means, explicit means that it's solved for y. So if you ever go all the way and you solve it for y, that's an explicit solution. However, you don't have to do that. You can just go with an implicit solution. And in fact, sometimes you have to leave it implicitly. Sometimes you can't solve it for y. So in those circumstances, you want to leave it like that. And sometimes actually the implicit solution tells you a little bit more. Like check out this one. Let's move that t squared over. If I rewrite this, I can rewrite it as y squared plus t squared equals c. And remember t, x, same deal. Do you recognize what these equations are? What kind of graphs those are?
It's a circle.
Yeah, those are circles. So what we know is that the solution curves are circles. And it's kind of clear from this. This one, not as much, but these are semicircles. The plus is the top half, the minus is the bottom half. But sometimes in the implicit form, it actually tells you a little bit more about what the solutions are. So think about what the slope field is going to have to look like. If we're going to get circles, that means that like in the first quadrant, all those slopes are going to be pointing this way to make us, or in the second quadrant, they're going to be pointing positive slope. Third quadrant, they're going to be negative slope. Fourth quadrant, they're going to be positive. And so I actually know a hell of a lot about this just from the implicit solution, the implicit form. All right, so just watch out for that. You don't necessarily have to go to y equals because sometimes you can't. And sometimes it's better not to because you can see what's going on.
And it's okay if we end up getting imaginary numbers from this if we have a y squared.
I don't know. What do you mean by that?
So, like, for example, if we have y squared equals, whatever, and, you take the square root and you end up getting imaginary numbers, if it was initial value problem, that's cool.
Okay, so no, it's actually not cool.
Okay.
Because we're dealing with real valued functions, and what that would tell you is that wherever you were getting those imaginary numbers are places where the graph doesn't exist.
Oh, so like it asymptotes or something at that area.
Asymptotes or yeah, the function stops somewhere. Like a good example would be like the square root function, right? The square root function starts at 0 and then goes. If you try to go the other direction, you get complex numbers, which is why we don't see the graph. So the same thing will happen here. If you run into a situation like here, for example, where it is possible that you would get negatives for certain t's, negatives in the square root, that just tells you the graph doesn't exist there. So think about like a circle. There is a leftmost and a rightmost point on a circle, because t's beyond that are going to lead to complex numbers.
Okay, that makes sense.
Okay, so complex numbers are not a problem, but they are a problem if we're talking about real valued functions. And in math, like if you go further on in math, you'll take classes where you do deal with complex valued functions, and they're totally fine. They just we have to do things differently with them. All right, so this was a pretty easy one in terms of the integrals, but it's a really good example to show you how quick it can be, just integrate both sides. And it also warns you about the explicit, implicit. So let's try another one. Let's go with y prime equals the square root of 1 minus y squared. And we'll even make this an initial value problem. We'll make it so that y of 0 equals 0. So we're going to find the solution that goes to the origin. All right, so I got to get those y's over. So I'm going to divide by the square root of 1 minus y squared. And what do I have left on the right-hand side?
1.
Yeah, that's just 1. So here's an example, kind of like when Bradley, when you asked about the can it equal 0, is it still separable? This is kind of like that, where there's just a number. And yeah, that's totally cool. It definitely works just fine that way. Okay, so now we need to integrate both sides. We need to find antiderivatives. Well, we'll start with the right, because that's easy. We'll go to x's this time. So that's just going to be an x plus c. What do we get on the left-hand side? Anybody remember what the integral of 1 over square root of 1 minus y squared is?
Inverse tangent?
Oh, close. It is an inverse trig function. It's just not tangent. Tangent's 1 over 1 plus y squared.
Inverse sine?
Yeah, it's inverse sine. This guy's sine inverse of y. All right, so here's our explicit or implicit form. And let's just go ahead and use the implicit form to help us find C. So we'll plug in our initial conditions. So we've got the inverse sine of 0 equals 0 plus C. Inverse sine of 0 is 0. So what we're left with is inverse sine of y equals x. So that's our implicit form. If we wanted to go explicit, that tells us that y is equal to sine of x.
That's kind of cool.
Yeah. And in fact, check it. You can see why y equaling sine of x is going to be a solution. We just go and plug it back in, right? Because y prime is cosine. So if we go back to the original differential equation, we'll have cosine of x. We want to know, does that equal the square root of 1 minus sine squared x?
It sure does.
Yeah, and from the Pythagorean identity, that's just a cosine squared, and its square root is cosine. All right, so I like the fact that Bradley just went, oh, that's kind of cool, because I think that's awesome. Like, look at this original differential equation. No way anyone would have ever thought, oh yeah, the solution is going to be just sine of x. Yeah, but it is. But it totally is. All right, so it is totally fine that there actually are no of the other variable. Like in this case, there were no x's or t's. You can still solve these with separation. And in fact, we have a name for that kind. So if you have a differential equation that's just y prime equals, let me just call it h of y, right? So it's only y's. These are called autonomous. So that's the name we give them. It's pronounced autonomous. It's spelled autonomous. And it gets that name. If you kind of break it down, auto is like a self. Nom is name. So these are equations that are self-named, meaning only y's. They're only named in terms of themselves. So all autonomous differential equations are separable. Hopefully you can see that. I mean, it should be pretty obvious, right? That if you've got this, you can separate it as just by dividing by the h of y. So if you ever have one that's only in terms of y, so an autonomous differential equation, you can pretty easily separate them and then go through the process. All right, so how are we feeling about this? Not too bad?
Pretty good.
Where are the problems going to be? Where do you think the difficulty is going to lie with these separable?
I'm guessing just integrating.
Yeah, and that does tend to be the issue. That once you separate it, what do you have in terms of y's? What do you have in terms of t's, x's? The challenge is going to be the integrating them. So that's going to be one of the big challenges. There's another kind of big challenge in these. It's the algebra. It's actually doing the algebra to separate it. You're going to see that that's a challenge as well. And this next example, I think, will kind of show you that. Let's look at this guy. Let's say we got y prime equals e to the x minus y. And what the hell? Let's make it a initial value problem. All right, so I need to separate this. I need to get it so that all my y's are on one side and all my x's are on the other side. So what do you guys think? Ideas?
Rewrite it as e to the x over e to the y.
All right, good. Totally make use of those rules of exponents. Subtraction is the same as division, because as soon as we do that, I'm sure you all see what happens. This becomes e to the y times y prime equals e to the x. So rules of exponents, rules of logs, those are going to be really key with these. Also, things like the trig identities. Because imagine if we had like sine of x plus y. Just in that form, you definitely can't separate it. But if you were to use the sum of angles identity, then you start getting things that are just sine of x and sine of y and cosine of x and cosine of y, and you can start manipulating. So just watch for that. But I guess Bradley just ruined all my fun. Thanks a lot, Bradley. Because now this is easy, right? Integrate both sides of this. Okay, so we get e to the y equals e to the x plus c. Okay, so let's plug in our initial condition. Y is equal to 1 when x is equal to 0. So that tells me that c is equal to 1. So we have e to the y equals e to the x plus 1. So that's an implicit form. But this one I would totally go to the explicit form. Because we know exponential functions are one-to-one, so you can always just equate their exponents. But yeah, there's the solution to this differential equation. Kind of crazy, right? Another one that you never would have guessed that the solution was going to be something this simple.
A line.
Yep. All right. Okay. So I think you see the process. I think you see what you need to do. It's just a matter of doing the algebra. So I don't think I'm going to torture you with another one unless you really want. I think instead what we'll do is we'll just go ahead and call it a day. Since we're already ahead of schedule, it's a beautiful day out there. Why don't you guys go out for a hike, go enjoy nature for a while, do something like that. Because again, monkey math. Totally monkey math, right? We're just doing the same thing again and again and again and again and again. It's just the same process over and over and over. Okay, so with that, I'm going to go ahead and stop our recording.